Whether you're conducting your GCSE geography fieldwork, snorkeling a coral reef, or even climbing Mount Everest, you can always rely on your trusty compass to point north. It has always pointed north, and it will continue to point north in the future. Or will it? If you were alive around 800,000 years ago, your compass would have pointed south. Why this switch happens, scientists aren't exactly sure, but let's explore some theories. So-called normal polarity is when a compass points north, and reverse polarity is when it points south. The Bruns-Matuyama reversal was our last geomagnetic reversal, and that happened approximately 780,000 years ago. This depends, of course, on which source you're looking at. So why has there been such a long gap since our last geomagnetic reversal? Is it possible that Armageddon is upon us and that the end is really nigh? Don't panic just yet. As we keen geographers know, our dynamic planet is constantly changing. For example, back when dinosaurs ruled the Earth, this magnetic pole reversal happened every 1 million years. Okay, so now we've established that we expect this pole pattern reversal to happen, and that it may take a little longer than we first expected. So let's take a look and see how it happens. So this brings us to paleomagnetism, the study of Earth's magnetic field through rocks. Earth's solid inner core is surrounded by a layer of fluid molten metal, known as its outer core. The magnetic field is created by electric currents caused by the flow of liquid metal in the outer core. We can tell how long it takes for Earth's ever-changing magnetic field to do a full 360-degree rotation through the polarity alignment of solidified manganite. Manganite is a type of rock that aligns itself with the direction of Earth's magnetic field. When manganite reaches 570 degrees C, which is known as the Curie point, the magnetic dipoles are free to move within the molten rock. When the manganite cools, the magnetic orientation is frozen in time, like our magnetic fossil. A perfect case study of this phenomena occurring would be at the new oceanic crust formed at the Mid-Atlantic Ridge constructive plate boundary. When molten lava rises through fissures in the lithosphere, the alignment process takes place, and over time we see a phenomenon known as magnetic striping, which occurs when alternating bands of oceanic crust have alternating magnetic polarity. A zebra crossing, whereby the dipoles are aligned with the direction of Earth's magnetic field. So, what can we disseminate from this magnetic striping? By studying paleomagnetism in sediment cores taken from solidified oceanic crust, we can determine the rate at which it takes for the plate boundaries to move, depending on the alignment of the oceanic crust. This process was key in proving American geologist Harry Hess's theory that new oceanic crust is continuously being formed. So, Earth's magnetic poles switch. What's the big deal? There are a myriad of ramifications that are associated with a reversal in Earth's polarity. Wildlife that rely on Earth's poles for navigation are affected. For example, salmon, birds, and even sea turtles. The polarity reversal also leads to a weakening of Earth's magnetic field, which exposes us to higher rates of radiation, which in theory could cause a mass extinction. But don't panic just yet though. Fortunately, the Bruns-Matuyama reversal showed no drastic decline in any plant or animal species. Paleomagnetic dating is important when understanding Earth's geological evolution, and hopefully further exploration of paleomagnetism will reveal many more of Earth's secrets.